So today we're going to start the more serious stuff, okay? So we start today what is known as the analysis of multi-cells in structures. Okay, so in here, let me see if it's better without the light. Yeah. Is better that way or the other way? Okay. So basically, I think that's something we already discussed, but in all your structures, Johnny, you make the assumption of thin and long slender members. Why is that? So like that? It's because all the equations you derive, basically, if you look at it, well, Johnny, what is the most critical load that you have? Shear. 50% chance you have, no? It's bending. So basically, all the equations you derive when you were like in doing solid mechanics, Johnny, you had that sentence like long and slender members. Okay. The main assumption, because you assume the stuff are long so they can bend. So if you're going to break it, you're going to break it by bending, no? Okay. If you have something that is very short and thin, how are you going to break it? Probably going to try to twist it. That will be shear, no? But most of the structure, basically building, I mean, wings, fuselage, they are long and slender compared to the in general, no? Okay. So as I would say thin. So that thin, long, slender basically implies that the main load is going to be bending. Okay, instead of shear. All right. So here I'm going to write something which is recalling. I'm not going to derive the equation again. So recalling the shear flow distribution equation in an idealized structure. Okay, so we're going to do this also later. I'm sure you have done some of it in Structures 1. We're going to do a bit more later on in this course, but I think it's better to start with the idealized. But basically what you have, a real structure can maybe, let's say, be under this form, but it's a lot more complicated to analyze it, but you can idealize it. I'm sure that's what you have done in Structures 1 for open sections. Okay, I'm doing here a closed section, but Johnny, you move all the area. Before, where basically you pass all the area that would be, let's say, of this stiffener, you model it by this one over here, by equivalent areas. Okay? Yeah, let's say, the shears would be whatever, the Q over here, Q V1, Q12 if you want, okay? So this is the idealization. I'm sure you have done this, no? Okay, but for open sections. So maybe you might remember or not remember that equation, but basically the equation is of the form, let's say Q of S is equal to negative, and it's quite long, the equation, so this is the full equation, XX minus VY IXY divided by IXX IYY minus IXY square, and this is important term over here. Integral 0 to S of X, yes, plus integral R equal to 1 to N to B sub R X sub R. And that's only the first term, minus Vy Iyy minus dx Ixy divided by Ixx Iyy minus Ixy squared. Integral 0 to s of Ty ds plus summation r equal to 1 to n b sub r y sub r. So I don't know if that, I mean, maybe you haven't done that equation that complicated. It simplifies a lot when you have a symmetric cross section. But does the kind of the equation look familiar a little bit? Yeah, okay. And this is the long and complicated one, but in most of our problems, we simplify it a lot, okay? Okay, so over here, for example, T is the panel thickness. So let's say here, this one, you see there's a panel in front of this one here. The B sub area is the equivalent area, that's the way they call it. This is the British term representing stiffeners or flange. V sub x, V sub y would be the shear forces. And the I's are the area moments of inertia. So one question, I like to ask this question. What is the definition of the moment of inertia? Physically, what does that represent?
The way the mass is distributed around that axis.
Correct. I mean, it's the mass mode of inertia is how the mass is distributed. Here would be the area. But what does it represent? So, for example, what equations you are familiar? Let's say you have some equations you remember, for example, stress, bending stress is equal to what? My over, Yeah. What does the I represents here? Just guess. This is due to what? Bending, no?
It's resistance.
Correct. No, you are resistance to resistance to bending or to rotation. Yeah, about that axis.
That's changing.
That is what?
That's a changing. So it bending or shearing, or did you? I think you were asking for I in general.
Yes. What is I in general?
It's resistance to change.
Okay, but it's resistance. So I agree with that one. Is resistant to change, not that much to change, but to bending or to rotate about one axis. So, for example, if you have a beam that is this way here, okay, let's say you have the load over here. Let's say you look at the cross section of the beam, okay? So this is going to bend. How is this going to bend? Let's say it bends this way. What is the I that you take? You take the I between these axes, no? Okay, so the I of this axis here, so the higher the I is, so the I represents how unlikely is this surface to rotate about this axis. Well, you want resistance to change, but resistance to bending, okay? So for example, if you have a structure, what do you want, a high I or low I? You want to have, here for stresses, for example. A high height, okay? I mean, this is what is generally the most common structure for beams is the I beams, okay? Why do they have that shape? Any idea?
Because they have a large moment of inertia.
Okay, but wouldn't it be better to have just a block like this? More material, no? Let's put it this way. What is the distribution here of the bending stress if we follow this equation? Is zero at the neutral axis and is bigger at the top and the bottom, no? So where do you want to have the material? Most of the material. Top and bottom, no? Okay, and this is, and what is the assumption you are making with this? Is that the shear, the structure is not going to break due to shear, because what would be the shear maximum? Okay, maybe you remember this one. The shear generally would be maximum at the center, no? Okay, but if you just look at bending, you want to have the most material to resist the stresses at the tip and the bottom, no? Yep. Okay, so again, just I think it's good to have a good physical understanding of what is the mode of inertia. So basically what you have done in structures one is probably calculated the shear distribution for open sections. I forgot one term here, okay, but I'm gonna have here. So you have open sections that would be of this shape, this way, where you have, for example, let's say, or this one, I'm sure this is the two type of, you have done most open sections. So here I'm going to put a Q sub naught, a value Q sub naught at the end of the equation here, okay? So for this section here, for open sections, you have Q sub naught equal to 0, because what does that mean? Is that here you could start calculating the shear from here, because you know what is the shear here will be 0, no? And you can start moving from this end to this end. Here, the same thing, you can start from here to here. However, if you have a cross section, do you have a point from where you can start? No. So what would be the normal procedure that we're going to follow? We're going to make a cut to make it an open section. But because we made the cut, they see you want some shear, residual shear that was in the structure, no? Before we make the cut. So here we have the Q sub naught is different than 0. So we're going to solve a problem, and then I will define a procedure. Okay, I will write down a general procedure. Okay, so the problem we're going to be solving is two cells. Structure. So let's see example. All right, so two cells. Let's see, we have here. Okay. All right, so we have the force that is being applied is a shear force here, VY, equal to 10,000 pounds. We have booms over here, so this will be 1, 2, 3, 4, 5, and 6. The height of the cells is all simple data, okay, is 10 inches. And the width of both of them is 10 inches and 10 inches. They are the same. So basically they are square. The thickness of all the flanges of stiffeners is 0.1 inch. Okay, and we have here B sub R. They are all equal to the same, will be equal to 5 inches square. And R is 1, 2, 3, up to 6, okay? So B1 equal B2 equal B3. And I think you were gonna need one extra term is that G, the torsion modulus of elasticity is 4 10 to the 6 PSI. Okay, so the question is to determine the shear flows in the structure, which is a wind box if you want, okay? Okay. Yes.
What's the thickness number?
0.1 inch. If you need, but then you need to stop me. I can probably zoom a little bit. Hopefully I'm not gonna mess anything. Is that a little bit better? Okay, but let me know because the page, okay. So basically something you have studied in Structures 1 is how to do this if the cross section was open. Okay, the structure was open. So here basically, what can we do to make it open? We can cut it, no? So we need to make how many cuts? We probably need to cut one cut on each one of the cells, no? Okay, so first step, make a cut. Why do we make a cut? So we can have a starting point where to calculate the shear flows. So step 1. Make a cut. Okay, so in this case, so I'm going to do very quick a figure. So let's say we make the cut in here. So the first structure, I'm not good at it. It should be a square, but just. Okay, so this is, again, this is 6. I'll go here 6, 1, 2, 3, 4, and 5. So if we make the cut over here, what's going to be the shear here? What is going to be Q12? 0. Right, perfect. I'm not asking anything complicated, okay? And what's going to be, let's say Q16 or Q61? I don't know, let's call it Q61. This one will be also 0, no? So why do we make the cut? So we have a starting point. Step 2. Now we can calculate the shear flows with the equation I gave you before. Okay, so in this problem, what do we have? We have Vx is equal to 0. We only have a Vy. Then a symmetric cross section. So what is that? What is that going to imply? It implies that IXY is equal to 0, no? I'm sure you have done that assumption many times before. Okay, so if we use these two conditions here and substitute into this equation, okay, what do we get? So the shear flow equation becomes of Q sub S. So this time we only have the Vy, so we're going to have minus Vy over Ixx And we are left with the two terms here, 0 to S Ty ds plus summation. This time will be R equal to what? 1 to 6, because we have 6 booms. E sub R sub R. Okay, so for example, in this equation you have here, this is 0, so this cancel is going to term. I is like 0, so all this term is going to cancel, no? All right, so we're only left with one term of a given function of the Vy. You see the Iy is going to cancel, you only have the Ixx, and you have these two terms. Okay, here it's important to see what is the meaning of each one of these two terms. So these terms here takes into consideration what? The shear, which in the booms, which is actually the same thing as saying flanges slash stiffness. So this is the effect of the booms 1, 2, 3, 4, 5, 6. And this term over here was T. So here, maybe I didn't put it, but you see, here's the skin, no? It's a panel. On each one of these things, these panels. So this is what's happened on the panels, the effects of the panels. Okay, there's another assumption that simplifies the equation a lot, and I don't know if you have done it before or not. But generally, when you have a structure, let's say of this, you need to do a design, let's say of a wing. Okay, so you have your spars and your ribs, no? What are the members that you assume will be carrying all the loads, or most of the loads? Spar, basically the spars and the ribs. You assume, as a factor of safety one, that the skin, which is giving basically what is the main function of the skin? Dissipate the load structurally, but the main function is to give the aerodynamic shape to the wing, no? Yeah, and to produce lift. So really the main function of the skin, if you think about it, is to produce lift. Okay, so one assumption you can do, which is done as simplifies the equations, is that you say that the skin or the panels are not going to resist any of the load. That all the loads will be resisted mostly by the ribs, by the spars and the ribs. Okay, so we put it here, assuming, and this is a very common assumption, okay? Assuming that the panels do not carry any load. Basically, that assumption is not perfectly correct to say, but mathematically it's working, is to say, let's say there is no skin, so you put T equal to 0. For the equation simplifies to what? And I'm sure this is the equation you have used most of the time. Q sub S will be equal to minus Vy over Ixx summation B sub R equal to 1 to 6 Y sub R. So does this equation kind of look familiar? Okay, it's good. I mean, you are building on what you learned from structures 1. So now, before applying this equation, we need to calculate what would be Ixx. Again, what would be Ixx physically? It will be the modular inertia about this axis that will be the resistance to bending, no? Okay, according to our definition. All right, so here we go. All right, so if I do here another sketch, I do a lot of figures because I believe that figures are worth like pages of words. Okay, so what is the name of this line over here that goes through the central? This is symmetric. In structure, then it will give it a different name. Perfect. And A neutral axis. What is the definition of the neutral axis? Or what happens at the neutral axis? Correct. The bending stress is zero, no? So remember, that's what we did. Remember what we discussed before about the I-beams? Well, they are the same. At the middle is zero, no? Is maximum at the top and the bottom. Perfect. Okay, here we know the area of all the booms. B sub R, we said was equal to 5 inches square. And that distance over here is 10 inches. So I don't know what to do too much. I don't want to do too much here on the figure, but let's say this will be our Y from the neutral axis. So if I look at the figure, we're gonna have what? Y sub 1 equal Y sub 2 equal Y sub 6. That will be equal to positive 5. Y sub 3 equal to Y sub 4 equal to Y sub 5 will be equal to negative 5.
Sorry, where we get, so BR equals 5 inches squared.
So what is the area out here of all these little circles over here? That basically is changing what would be here the structural member, like the flange of the stiffener.
Okay,
We substituted, okay?
okay, and so then,
Okay, so this is just the distance from this line, from the neutral axis to the top and the bottom, okay?
okay,
And we do that because you can approximate, I'm pretty sure I've done this, let me know if you haven't. You can approximate the moment of inertia about this axis here. If you want, this is X and Y. IXX, what is the general definition is? The real definition of the area moment of inertia is Y squared dA, no? Okay, but we can approximate this as just being equal to what? To do the integral, it's like doing the summation sign. So this will be B sub R, Y sub R squared equal 1 to 6. So basically this should be equal to what? B1 Y1 squared plus B2 Y2 squared plus B3 Y3 squared plus blah 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 until D6 Y6 squared. And if you do that calculation, you have that the moment of inertia about the x-axis is equal to 750 inch to the fourth. I mean, I'm pretty sure you have done this before as well. Okay? Okay, so now everything, we know Vy, we know Ixx, we can start starting from one point, we can start calculating what will be Q12, Q23, Q45, Q56, and Q7. All right. So over here, we made the cut. So let's start from here. What do we know? We know Q12 is equal to what? 0, no? Because that's where we made the cut. All right, Q12, 0. Now we can do Q23. So Q23 will be equal to what? Q12, whatever was before. What is the equation that we have here? Minus Vy over Ixx. This will be equal to what? We start from which point? From which room? 2, no? So this will be B2. Y sub 2. Is that clear what we did over here? We go from here to here. So it's Q12 plus Q23. We start from this one. So it's B2, Y2. So this will be equal to what? 0. Dy is equal to 10,000 by 750. This B sub 2. All the B's are equal to the same, no? So 5. What will be Y sub 2? 5. Okay. So if you do the calculation for this, that gives you Q23 equal to negative. I mean, it's 1,000 divided by 3, but you want 333.3 pounds per inch. Okay, so similarly, we can do what? Q34 will be equal to what? Q23 minus Vy over Ixx, B of what? B3, Y3. So let's see. I'm sure you understood, but let's see if one of the assumptions, remember what we said about the design on the first 2 lectures, if the load is going up and down, I mean, over here, what should be the members that will be resisting the load? The vertical. You agree that this one, probably we should not give any load, no? So if this is 0, what should we get for 3/4? 0. So let's see what we get. Okay, making that assumption. So here we have Q23 is equal to minus 333.3. Here we have again minus 10,000 divided by 750. B3 is 5. But this time, what is Y3? Negative 5. So basically, it will just be the opposite than this one, no? So here we're going to get Q34 equal to 0. Surprise, because that makes sense with the assumption that only the loads, the members which are in the direction of the loads will be carrying the load, no? Okay? All right, so we have 3, 4. Now we can go to, we need to be careful here with 4, 5, because 1, 4 is common to the both cells. So let's see what happens. Maybe when we do another figure. The next one we're gonna have is Q14. But let me do the figure here again. One, 2, 3, 4, 5, and 6. And here we know that Q12 is 0, and Q61 or Q16 is equal to 0. Okay, so if we look at Q14, this is like electrical engineering. What would be the current going to 14? Should be equal to what? Q12 plus Q61, no? Minus this time we do the V1 over IXX. What would be the B? From B1, no? So B1 Y1 as before. What is Q12 and Q61? 0 and 0. You see, I still do the figures, so you see both of these two should be equal to 0. So if we do again the same calculation, it's all the time the same terms. Minus 10,000 divided by 750. B1 is 5 and Y1 is 5 as well. So this gives you that Q14 is equal to negative 333.3 pound per inch. Okay, now that we have Q12, Q23, Q34, Q14, we can move from 4 to 5. So I'll be Q45 will be equal to what? Q34 plus Q14 minus B1 over IXX, of which B before Y4. Okay? What was Q34? I mean, one was 0 as well, no? It's not one of the vertical loads. So we get minus 333.3 minus 10,000. I mean, what should we get? 0, okay? Minus 750 times 5 times this time minus 5. So as expected, we get Q45 equal to 0. Okay, and finally, Q56 will be equal to what? Q45 minus Vy over IXX, B of what? B5, Y5. So this is going to give you 0 minus 10,000 divided by 750 times 5. What is y sub 5? Is negative 5. So again, this is going to yield to Q6 equal to 333.3 LP per inch. Okay, I mean, maybe it's not a good thing that I tell you this, but I think it's better to have the understanding. We really needed to do all these calculations to know that. Okay, if we make the assumption as we did on the previous section, only those three members will be carrying the load, no? So what will be the load? Will be 10,000 divided by 3, which will be 3,333. If we calculate that per unit length, what is the length of this one here? 10. We divide 3,333.3 by 10. What do we get? 333.3, no? Yeah, so you see. Just by logic, you can calculate what is happening, no? But want to be details, you have all this stuff. Okay. So now, something I did not mention is that here, what is my page? Let's see, first page here. Here we made the cuts. But before we make it, because we made the cuts, we know we started. But I did not put it here on the equation. What's happening over here when you have a cross section? You have inside some type of initial or residual shear flow, no? That we're gonna have to calculate because it's not zero. There's the cut is not there, so there's some. This should replace the cuts. Okay. So step 3. We're going to assume an unknown shear flow in each cell assume an unknown shear flow in each cell due to torsion producing the same angle of twist. So let's see. Let me just do the figure now again. Another figure. So now I do the figure without the cuts. This and this. Still have those booms. That will be 1, 2, 3, 4, 5, 6. I'm going to assume a constant shear flow on each one of the cells, Q1 and Q2. So Q1, 2 will be the assume. Maybe I forgot to this before, but assume constant is important. Assume constant shear flows. Okay, on each one of the cells. Then we have to do the figure on the next page anyway, so. And we're going to do the same angle of twist. Which is the equation, so d theta z of the first cell needs to be equal to the angle of twist of the second cell. Where the expression for the angle of twist, a bit complicated, that one, is 1 over 2a integral across the cross section. That's why I do the little circle across the cross, the integration sign of q over gt ds.
bottom there is it, Q over what? 60.
D theta dz equal 1/2a. This is Q divided by G, GT, the thickness, ds. Okay, so here it is. Two ways to do this. Personally, I think this is the best way to do it. So let me just redo the figure. Yeah. So we know here we have Q1. We knew here we have Q2. And then if you remember here we had, I need to put the number again. So this is a little bit tedious, but this is where it's good to use MATLAB because you do it once for one of the problem and all the problems are kind of similar. So you only need to change the values. So what do we have for Q12 over here? If you remember, all these ones were 0 here, no? Yeah. Okay. And then let's see, what do we have for 14? So Q14 was negative. So that means that actually if we needed to plot it, it would be going. Okay, so you put it here, let's say Q14 equals 333.3. Okay, so the other one would be Q56. What do we have for Q56? 333. So this one is also up, no? It's not changing the sign. So 300. So Q56. Okay, does that make sense or not? What was our problem, initial problem? Yeah, so, and now Q23 should go up or down, do you think? What do we have for Q23? Probably we have negative value, no, if I'm correct. Yes, so it's also going up as being Q23 equal to 333.3. Okay, so now what we do, we're going to define a new shear flow that we call Q12. Where Q12 is equal to what? Q12 plus the Q, the constant shear flow that we assume to torsion in 1, Q sub 1. So in our case, this is equal to 0. So Q12 is the same thing as Q1. And we keep doing the same thing. Now we need to be careful. What would be Q23? Q123. Okay, but you see, these two will be going on the opposite direction, no? So this will all really be equal to negative to make it go down. So this should be on the opposite side, minus 33.3 plus Q1. Yeah? Okay, you see that going on the opposite direction. Then Q bar 34 should be equal to Q34, which is 0 plus Q1. Okay, now comes probably the most complicated one. Let me put it over here. Let me jump one line. Q bar for 1. We go to what?
Q1
Q1 4, correct?
minus Q2.
Correct. Plus Q sub 1. Perfect. Minus Q2. So basically that means that this will be equal to negative 333.3 plus Q bar 1 minus Q2. Now the other one will be easy. Q bar 45 will be what? Q45, which we know is 0, plus what? Q2, perfect. Q bar 56 will be equal to Q56 plus Q2. So this will be equal to 333.3 plus Q2. And finally, Q61 will be equal to Q, if you want 61, plus Q2. And we know Q61 is 0. So now what is the assumption? So that each cell must have the same angle of twist. So that means d theta dz for 1 must be equal to d theta e for 2. Okay, well, just recopying the equation from before, we know that d theta dz is equal to 1 over 2a integral throughout the whole cross section of Q divided by GT. Yes. Okay, I'm not sure you remember that equation, or if you use that equation in structures 1. I'm not sure about that. Basically, the one of the angle of twist, okay? Okay, so let's look at the angle of twist for the first cell. This one over here. If you want, let's call this one 1 and this one 2 over here, okay? You want to add it. So cell 1, we're going to have d theta z for the first cell. So here I can factor out 1 over 2. A1 is the area of this one. Okay. So actually in this case would be easy. What will be 10 times 10, no? Okay. Now, since the whole structure is made of the same material, I can factor out the G over here as well. Can move the G over here outside. But the reason why they put it inside is because you might have maybe this member which is made of different material than this one, no? Yeah. But in this case, they're all made of the same material, so that's why we can pull it out. Now, if I try to do the integration of this one over here, of Q, so we have to take care of, and even the T, we can put it outside because the same thickness for all the elements. Oops. It's also constant for all of them, no? Let's see what is the problem statements. Yeah, you see here, the T is the same for all of them, okay? Same final thickness. Okay, so now basically what I need to do is to go around the structures one about this cell by looking at the Q times ds. What is the distance for each one of these cells? What is this one? 10, 10, 10, and 10, no? Yeah, so if you want, I can factor at the end by the 10. And what I need to do now is what? Q bar 1, 2, Q bar 2, 3, Q bar 3, 4, Q bar 4, 1, no? Yeah, if I write down the equation with this, so Q bar 1, 2 plus Q bar 3 plus Q bar 3, 4 plus Q bar 4, 1 times 10 because they're all the same. What did he do next? We need to substitute this Q bar 1, 2 by whatever we calculated before, no? Okay, so this will be what? 1 over 2 A1 GT. Probably I have enough space to put in one line. I don't think so, but what is Q bar 1, 2? Q1. Q bar 2, 3 will be minus 3, 3, 3 plus Q1. Q3, 4 is Q1. And Q4, 1 is negative 333.3 plus Q1 minus Q2. So if you do the calculation, this is going to give you d theta dz 1 to be equal to put the 10. Okay. 10 divided by 2 A1 GT times 4 yeah, I was looking at because it should cancel. So which one is it? This one is positive. Okay. Well, what did I do here then? Let me go back here. Two, 4, 1. Okay. So basically, we are left here with 4, 2, 1 minus Q2. Okay, let's say this is equation I over here. Yeah, you're right here for that. So also change it over here on top. Okay. Yeah, got it wrong. So 19. Now we do exactly the same process for the second cell will be d theta dz of the second cell, which is this one over here. Okay, so this is going to give us what? 1 over 2 A2 GT. I start from this one, Q bar for 5 plus Q bar 5.6 plus Q bar 6.1 plus Q bar 1.4 times 10 because other members are 10. I just substitute, so it will give you 1 over will give you before same notation as before, it should give you 10 over 2 A2 GT times Q45 will be Q2 333.3 plus Q2 plus Q2 plus minus 333.3. Is it this plus, no? I think I did it wrong here. Minus Q1 plus Q2. So this gives you d theta EZ of 2 equals to 10 over 2 A2 dt of 4 Q sub 2 minus Q sub 1. And let's say that would be Roman 2. Okay, so now we equate basically 1 2, and what do we get? We get 10 divided by 2 A sub 2 GT for Q1 minus Q2 equals to 10 over 2. Sorry, this should be A sub 1. A sub 2 GT for Q2 this Q sub 1. So that makes sense here. At least that makes sense. Since the structure is symmetric, okay, what can you expect about if you want the assumed shear flow in each one of the cells? They should be equal, no? Okay, so that's probably what we're going to get, as you can see at the equation. So you see here that A1 equals A2. So you can cancel out these two terms over here. They cancel to each other, which means at the end that we have 4 Q1 minus Q2 equal to 4 Q sub 2 minus Q1, which basically this is going to give you that, let's see, 5 Q1 equals to 5 or basically that means Q1 equal Q2, which is what we were expecting. I can rewrite this as the equation Q1 minus Q2 equal to 0. Let's call this equation, let's see what I've been calling here. Let's call this equation capital A, okay? And so it will be different. Okay, so let's go back from the beginning a bit. So we have two cells, closed cells. We make the two cuts, okay? We calculate the shear flows. Now we make the assumption that each one of the cells need to have the same angle of twist. Okay, so the assumption of making that each cell will have the same angle of twist is giving us one equation. Yeah, this one here. How many unknowns we have in that equation? Not complicated, two, no? Okay, so what do we need to do in order to be able to solve? Yeah, to find another equation. So basically, that's why this is statically indeterminated, because we need additional equations. So the next equation we're going to be using, step 4. Maybe I should have done the other one first. Would be more logical on the procedure. But that's the way we did it. Not a big deal. So step 4. The last equation is obtain taking moments such that you can say that the moment created by the external force using the counterclockwise, I mean, you can change the sign convention, will be equal to the moment created by the internal force. So basically, very the more understanding, if you apply this force over here, you agree that this force over here is the one that is going to be resisted by all the shear flows in these panels. Correct? And that's why we have this 10,033 was then divided 333, 333, 333, but we needed to introduce the Q1 and Q2 because they were closed out, no? But all the effects that are happening due to the shear should counter-react the effect of this force. Okay, so what we can do is take the effect of this force, the moment created by this force about a point, okay, and say that must be equal because it needs to be counter-reacted by the moment created by all the shear forces inside the two cells. Yeah, that's basically what we're doing next. Okay, so let's see about which point we're doing this. Let's see about which point I did it. I probably did about 0.4, yes, about half. Okay, so step 4. Let me go to the next page. Oh, we only have 5 minutes. Okay. All right, so let's build up. So basically, we have the measure of the external moment be equal to the moment of the internal moments about 0.4. Okay, so all right, let me do here a quick figure. Otherwise, going to be If we don't finish, we don't finish, okay? I don't want to rush it either. Okay, and all the distances at 10, okay? All these ones at 10, so. So 0.4 is this one over here. So what is the moment created by the 10,000 shear force about 0.4? So we know it's 10,000. What is the value of the arm? 10. Would that be positive or negative?
Positive.
Positive, okay? So we have that one. Now we need to be a little bit more careful because what do we have? What is the value of the force between Q1 and 2? With the Q 1, 2 times what? Times 10, that will be the value of the force, no? What will be the value of the arm? If you want, I just do this slow. This is force. This is arm. Okay, we do the same thing with all the other ones, plus Q bar to 3 times 10. What will be the arm? 10 as well, no? Okay, we do the same thing for the other ones. Q34 will be 0 because it goes through 0.4. Q45 will be 0. We do Q bar 56 times 10 times 10 and Q bar 61 times 10 times 10. Okay, if we substitute the Q12 by which values? The one we had before, no? The Q1, Q2, plus minus the 133, the one we calculated before. By what are they? What are those values of Qs? 1. 17, where's my page 18? There's one I'm missing. These ones. The Q bars will be all these terms over here, no? Okay, that's why I say to use MATLAB. So if we substitute all these values, you're gonna get that you get 1,000 equals to 2 Q1 plus 2 Q2. Or you get the equation Q1 plus Q2 equal to 500. And this will be our equation here. The system of 1 and 2, which is basically what? Q1 minus Q2 equal to 0, and Q1 plus Q2 equal to 500. So that's very easy. This is going to give what? Q1 equal Q2 equal to per pound inch. So just give me a few seconds. So finally, the shear flow distribution will be what? One, two, three, four, five, 6. So basically, in 1, 2, what was the shear flow due to a 10,000 in 1, 2, 1, 6, 4, 5, and 3, 4, 1, 0, no? So what should be now Q12 then? Would be equal to the 250, no? Yeah, this one the same thing. 2, 3, 4 will be 250. Q45 will be 250. And Q61. But the bars, so here should be the Q bars, okay? Q bars, not the Q. The Q bars will be 250. Now, you remember we have the 333.3. Okay? So what's going to happen when the sign, so for this one, here we have Q bar 5.6 will be equal to 583.3. The one in the middle becomes 333.3. The one at this end becomes 83.3. Okay, so sorry for finishing up a little bit on a rush, but better than to start next time, okay? Question. So my advice is that when you do the assignment for this, use Maven, okay? Because it's all the time the same process, no? MATLAB, I mean. Yes. What is this? Page 1.
After code, so like submissions, it's like, or
I mean, you attach it, like you can attach it if you want. No, I mean, personally, for the assignments, it's not that important. You can just say using my MATLAB course, this is what I got. Yeah, it's not that important. Yeah. So, do you have any resources for some kind of reviewing that as well? Yeah, I was of course like we smelled this. Did you check did you set up the video last one on campus? I see it's an project. No, it's on the first lecture, the second lecture.
your classes.
I'll put like a link to do the NASA model for the example we did in class. Okay, I'll look at that. Okay, so remember, yeah, I remember. Yeah. So if you look at that, it's going to take you to my YouTube channel. There is how to do the NASA of everything we do in class. Okay, so probably if you need more, I can give you more. Thank you so much. I'll leave it to that. Have a good one. Yeah.
So you're like-
Oh, it's fine.